Hi again. So we just solved this problem. It took 47 minutes. So the last video was me solving this live, coding, debugging, as well as time and space, complexity, and looking at top solutions. So I thought I would just make another quick, hopefully 10 minutes or 15 minutes video to explain the algorithm. So if you don't want to see this entire coding and thought process, this will just be the explanation video. Alright, let's get into it. So minimum size subarray sum. So this was part of the first sliding window problem in this top interview, 150 questions. So we want to think sliding window. Okay, so we have a window. This window will be moving towards right or left. It could be expanding or shrinking. So that's sliding window. So you can pause and read the question first if you haven't. Let's get right into how we should think about this. So we have this example and this target. So we start from the beginning. Let's say the starting window is 2. We see 2 is not reaching the target. So we expand this window, we get 5. Still not reaching the target. We expand one more, 6, still not there, 8. Now we have a window that works. We reach the target. So what do we do from here? So we are looking for the minimum length of a subarray that reaches that target. So when we have this window, if we continue to expand to the right, of course that would also satisfy the target because all this is an array of positive integers only. So there's no use to expand to the right because it will only be longer than what we have now. So what do we do? What if we shrink it from the left? Okay, we have, this is 8, this is 6. So we shrink the window from the left, now we have 6. So 6 doesn't satisfy this target anymore. And now we continue to expand to the right until we find that window that satisfies the target. So we have 6 here, and now we have 10. So 10 exceeds target. So we don't need to do anything more from the right. We can now shrink the window from the left and see if we have a smaller window that still satisfies the target. So we shrink this window to only 1, 2, 4, which gives us 7, and that's good. Oh, I forgot to say that along this way, every time we find a window that satisfies our target, we should also store the length. So after all this traversal, we will be able to get the minimum length. So before, when we were doing this, so that's 6, 8. There we had length 4. Now we have 6, not reaching the target. We have 10, also length 4 at the target. So we are not improving our minimum length right now. But once we shrink this window from the left, now we only have length 3. So we need to store this. Okay, so what do we do when we have this window? we can either expand to the right or shrink one more from the left, because at this moment we know that if we expand to the right, that will now give us a better solution, and if we take away the furthest left one, since they're all positive, that will give us less than the target. So no matter what we do, we need to move this window to the right like this. So we were here, let's say we go towards the right, we see that's exceeding target, so we can shrink this from the left again. Now we have 9, so that's exceeding target. So what do we do here? We see there's still length 3. So every time we find a window that exceeds or reaches the target, we shrink it from the left to see if we can find a smaller window that still satisfies the target. Okay, so now this window is only for 3, length 2, which is better than what we had before, so that will be updated. And length 2, sum is 7, this hits our target. And what do we do then? So there is no more element to the right, so we will not do anything more there. We can, well, since this is exactly the target, we know that if we shrink it, it wouldn't reach. But let's say if this had been 4, 7, then we could still shrink this from the left and be left with 7, which will meet the target. So when we're here, the right hand side is finished, it's ready, there's no more we can do, but the left hand side will continue to go until it reaches the last element as well, because we need to check the case where the last element could just simply be exceeding or reaching target, and then we have a length of 1. Okay, so that's the idea. That's how we are checking this. So the algorithm does exactly this. We have a left, right pointer. The result is this minimum length we want. So it starts off as the infinity or the maximum integer, depending on your language. So it starts out really big because we are looking to do this min function. If there is no subarray, we want to return 0. So we need to have some kind of marker to mark the case when there is simply no solution, when there is no subarray that satisfies the target. If we had started out this with the length of the input, that would not work, because then we would have this result as length of the input, and we don't know if it's because the minimum length of the subarray that satisfies the target is that entire array, or it's because we cannot find any. So it cannot be the length of nums. And it also cannot be 0, because we want to find the minimum. If it's 0, it will always give us that 0. Then we have no way to return 0 when there is no such subarray, and return the length when there is. Okay, so the window starts out with the first element. So we have these two pointers, they cannot go outside of this array or list in this case. So we start out with this first element as our window. If the window is smaller than the target, then we want to move right pointer, increment that, which means we are expanding our window towards the right, and then we want to update our window now to include this new element to see what's the sum now. So this will we will encounter this later, so we will talk about that later. So for now, if it's smaller than target, we expand the window and move our pointer. So we're gonna do this, and we will be doing this until window equals or bigger than target. Then we go to this part. So what happens? So that's when this happens. We have 8, which is bigger than 7. So what happens then? Result will be the minimum of the last minimum result, and the current length, which is right minus left plus 1. So those will be 3, 0, plus 1, because this is 4. So that is updating the result. And what do we do here? We know that this window satisfies, so we try to shrink it from the left. So let's remove the furthest left element, which is standing at left index. So this removes it from the window. We move the left pointer. So now we have shrunk this window from the left. So now we go to the next round. If this window is still bigger or equal, it will continue to do it until it's smaller again. Then we go into this part. Then we expand to the right. So we are gonna do this until right pointer is at the last index. Actually, let's try this. What if since right pointer will go towards the last index, oh, I see. Okay. We need to have it there because when the right pointer is at the last index, we do not want to do right plus 1 anymore, and then because that will give us the index of the range. So when that is there, we can break wait a second. So we need to break out of this while loop. Oh, okay. This is what I'm missing. So for the case when if right pointer is already at the last index and this window is still smaller than target, then it's actually nothing we can do because we cannot expand it anymore. We can only shrink it, and shrinking it only gives us less sum. So in that case, we just have to break out of this while loop. There is nothing more to check. And if left pointer is at the last index, let's see why this is necessary then. So if right is at the last index, we will break. If left is at the last index, So when left is at the last index, is it guaranteed that right is also at the last index? So this window can at most shrink to one element. So I'm thinking maybe we don't need that part. Let's check. Okay, yes. It's a little bit of refactoring, that's good. Okay, so we don't need that part because once right is at the last index, that's when we break out of it. And this window will at most shrink to this one element. So left index will never actually go over the right index. Now, what if left and right are both here, and this is, let's say it's 8, so it is bigger than the target. Wouldn't that be interesting? Okay, what if this is 8 and both left and right are standing here? Would that happen? Yes, that could happen. You could have this window 6 and then plus 8, and then it will be shrinking like this. So this will be 8 and both left and right will be standing here. So that window exceeds target, so it will come in here, result, it will be 1 there, window minus left, that'll be 0, and left will actually go over right. That will be an interesting case. Could that happen? 8 is here. I wonder if there are no test cases that test that specific scenario. Oh, I wish I could use my own test cases. Is that possible? No. I mean, of course we can test it ourselves elsewhere. Okay. That would be okay. So if right is there, left is here. Would that break this? So if this was 8 and left and right are both standing there, window would be 0. And then left goes there, and we come in here, right also goes there, so then the window becomes the next number. So I guess it doesn't break the code. But it's not logically perfect. Alright, okay, interesting case. Okay, I think I have explained everything here now. And in the end, we want to check if we have found anything. We would have updated here. The result is no longer the infinity. And then we just return the result. But if we haven't found anything, which means the window never reaches the target or exceeds, then we will never go in here, so this result will never be updated. It will still be the math.inf, so that's when we return 0. I thought I would make a short 15 minutes video, but now it's been 20 minutes. Alright. I have already gone over time and space complexity in the last video. Maybe I can just summarize very quickly here. If you want the details, you can look at the last video. I will link it below. So time, this is a linear solution because, interestingly, when we're doing this sliding window, let's have a look at the left and right pointer. So we are extending to the right and we're shrinking from the left. So for each element, it can only get one expanding and one shrinking at most. So we have this window, it can only expand like that. It will not go back, it will only go towards the right. So each of them will at most just get traversed once. And then when we're shrinking from the left, even if we had this entire thing, it would just be shrinking like this. So it can only be shrunk once also. So for each element, it will at most be one expanding, one shrinking. And we will look at all elements. So that's linear. And space is constant because we're not using any data structure, just some variables. So linear time, constant space. Alright, I will conclude this video here. If you'd like to see the entire coding and thought process of solving this problem, please check out my first video, and I'll see you in the next one.